Ladies and gentlemen, this lecture on extensional tectonics and continental breakup is subdivided into two sections. In this first section, we are talking about extensional structures, how they look like, what kind of varieties we might commonly find in nature. In the second part, we are going to talk about different types of continental breakup. And here in the background image, you see a classical setting of continental breakup forming a typical triple point junction here in the Afar region with two arms already developing oceanic crust, the Gulf of Aden here and the Red Sea, and the third arm of this triple point points down to the southwest into the East African Rift Zone. Extensional tectonics are closely related to the Wilson cycle, and here these first two stages of the Wilson cycle show what we are going to talk about. The weakening of continental lithosphere and the divergence of parts of the continent away from each other form rift graben structures that thin out the continental lithosphere and may eventually lead to the formation of new oceanic basins with mid-oceanic ridges along of which the oceanic basin grows. On either side of the oceans, passive margins are forming which might continue in further spreading, but eventually oceans will be consumed by subduction on either or both sides of such oceans, and that then forms Andean type continental margins, followed by continent collision and by the erosion of the mountain belts that form in this stage. This leaves us in the end again with a consolidated continental landmass that might undergo a new plate tectonic cycle. The extensional stages that we are going to talk about are found typically in intracontinental rifts, in mid-oceanic spreading zones, but also in back arc basins, which we find behind subduction zones in the upper plates, back arc behind magmatic arcs. And such back arc basins can be continental or they can be intraoceanic, as we see here. These subduction zones are the cause for the extension in the back arc. We come back to that at a later stage in the course. Coming back to the Red Sea Afar Rift Zone environment that we have seen on our cover slide, we see here a typical configuration of three arms of extensional tectonics. Two of them are quite advanced and form the oceanic basins of the Gulf of Aden and the Red Sea. The third one points into East Africa, and when we look at this map here from Franco Piranio's work in 2004, we can see that the Afar triangle that we see here with the two active and successful rifts and the third arm into the East African rift are located in the vicinity of Mantle plumes. We see here the Afar plume. Here in southeastern Africa we see the Lebombo-Sabi junction, the Lebombo plume. Tristan, the Cunha plume, is here one of the plumes responsible for the breakup of Africa and South America, and the same applies here for the Benue plume in the Gulf of Guinea. These are only the recently active mantle plumes in Africa. There are a number of older age Archean to Proterozoic plume heads are indicated here in dark gray color, and I believe one could draw a number more in the West African regions. Here we see a map of the region with the East African rift and a close-up of the box that we see here on the left-hand side. More detail is provided over here. This figure comes from van der Ploem and Marschak's beautiful textbook Earth structure. All the figures that I show in this slideshow indicated with PM refer to figures from this textbook. We see here that the East African rift coming from the Afar plume here in the north moves to the southwest and then splits up into two arms, a western arm and an eastern arm that cross over in southern Tanzania and northern Malawi and form these two independent drift arms that we see here better on the right hand side. There is very significant volcanic activity in the central part of the Eastern Rift. Mount Kilimanjaro, Mount Kenya and Mount Nyiragongo in DRC are the most prominent and active volcanoes. But we see here the graben system, the extensional rift system, transects all the way and in many places forms very significant freshwater reservoirs like Lake Nyasa, Lake Tanganyika. Lake Victoria is partly related to rifting, but Lake Albert and Lake Kivu here between Rwanda and DRC are definitely in the middle of these rift graben systems. Here we see a satellite image of the Afar region, and when we look here in this area we see color changes. These color changes are related to high topography in southern Yemen and in large parts of Ethiopia. These are topographic high areas. The topographic height of these regions is related to heat input from the Afar plume, and we know that heating up the Earth crust lowers the density and that increases buoyancy, which results in high topographic terrain. On the ground in the arid areas we can see the results of extensional tectonics. We see here gaseous of extensional faults that have recently formed by tectonic events. So this is a tectonically active area. Here is a much more spectacular example of a deep gash that has formed as a result of extensional tectonics. And closer to the surface you see that as very prominent topographic features. You see here the persons on the left hand side for scale. Here we see a smaller scale feature that shows one of the typical effects, and that is the tilting of parts of the surface that once was an even terrain that you see here, affected by extensional tectonics during an earthquake. And some of these segments show that the surface is now inclined into either direction, either this way or that way. And a possible explanation for such a tilting of segments in fault zones is Listric faulting. Here we see a schematic illustration what Listric faulting means. It means that normal faults are curving. They are steep close to the surface but are curving to greater depth, and that makes layers rotate. And we see here the black marker layer, initially horizontal, shows now increased tilting with increased displacement along such curving fault planes. The tilting of these blocks here might be related to such processes. Listric faults are not the only typical feature that we might find in extensional tectonics. We also might find standard horst and graben structures where the conjugated normal faults are in fact planar. They are not curving, and we might find combinations of Listric faults and planar normal faults in different rift zones or in different parts of the same rift zone. What they have in common is that they extend laterally the crust, and we are creating space at the surface in the form of sedimentary basins. We see here within the graben structures or within the half grabens here on top of Listric faults, we create space in which new sediments can be deposited, and typically these sediments don't come from far. They come from the rift shoulders, they come from the host structures where erosion will transport them into the nearby topographic low of the extensional basin. Where we have these typical detachment faults that are associated with half-grabens and with Listric faults, we would distinguish an upper plate and a lower plate. And also Van der Plume and Marschak mark the boundary between the upper plate and the lower plate somewhere here. Strictly speaking, everything that is on top of the detachment would belong to the upper plate. That would mean also the slices that we see here, the rotated, tilted blocks that form these ranges and basins, are strictly speaking part of the upper plate. Here we see slight variations of the features that we already have seen. On the left-hand side we see bookshelf structures. This is simply a Listric detachment fault that is overlain by a set of blocks separated from each other along planar faults. If normal displacement takes place along this Listric fault, as we see over here, we will find tilting of these planar blocks in a way similar to tilted books on a bookshelf. The part that is somewhat unrealistic is of course the formation of open space here at depth. Such space would certainly be filled by crushed material of these individual fault blocks. Over here we see the classical segmentation along a set of Listric faults, and these Listric blocks do not have the problem of this apparent formation of open space at depth. They slide simply along the curving layers downwards, tilting increasingly the marker horizon that we have seen as a horizontal layer here in the stage before faulting started. A typical structure that is related to faulting along Listric faults is the rollover anticline. The rollover anticline is simply a gravity-driven structure that responds to the displacement of the upper plate compared to the lower plate along the curving detachment. Obviously, such a gap cannot form in this geometry. What would happen is simply that the upper plate drops continuously down and then forms an apparent fold. Here we see that extensional structures can be more complex than what we have seen on the rather simplified illustrations on previous slides. Here we see a combination of normal faults on top of a large Listric detachment fault, and here we distinguish synthetic and antithetic normal faults. The synthetic normal faults would show the same displacement direction as the detachment, and the antithetic faults would show the opposite, the conjugated displacement direction, top to the left in this case versus top to the right for the synthetic ones. So here, that is where we end our first section of extensional structures. We have looked at the structures themselves, and in the next section we are going to look at how these structures contribute to different types of continental breakup.